Hello, this is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Limit Definition of the Derivative. Recall that we talked about you can find average rates of time change, but you can also find instantaneous rates of change, and an instantaneous rate of change is found by thinking about the slope of the tangent line. And so this curve is going along like this, but the slope of the tangent line here is telling you how fast the curve is changing exactly at that point. It's similar to riding along the function like you're in a coaster, and that's your line of sight, is that direction. So let's talk about an applied example, word problem. This is talking about how the number of Social Security beneficiaries grows over the years, and you see that's the blue curve. But we're now going to talk about the rate of change. How fast are they changing at certain times? So we're going to estimate what is the slope at P1 and what is the slope at P2. So you have this information. You're supposed to find out the answers to these 2 points, and be aware that this is in millions on that axis. You know what to do. Let's see how you did. So you look at the slopes here. The slope is 1/2, and here the slope is 1.15. And when you change the units, you see that that means that at this point, when t was 10, it was increasing at 0.5 million, or 500,000 per year. At the other point, it was increasing at 1.15 million, or this many per year. So we're going to define then the slope of the tangent line is going to be the limit of the slopes of the secant lines. So, and this is just how we did that approximation. We were talking about finding how fast the thing was going at 2, the train was going at 2, and we talked, oh, how about from 2 to 4, and then from 2 to 3, and then from 2 to 2.5, and so on. So here's the point we're interested in right here. That's where we're drawing the tangent line, where we pick point Q1 here, Q2 here, Q3 here, so on and so forth, and these are getting closer and closer, and I compute the slopes of, and these are called secant lines, so they cut through the curve. But the limit of these, as you approach this point, is going to be the slope of the tangent line. Let's zoom in and see how we go about calculating that. So suppose this is the point we're interested in. We're going to call it x, and we'll move just a little ways down, and we'll call this x plus h. Here we're letting h be positive. H could be negative as well, going the other way. Let's just stay with this. So we got these two, and when I plug the value in here, I get x, f of x, and when I plug x plus h in here, I get x plus h, f of x plus h, and that is riding on the curve y equals f of x. So the slope of that tangent line is going to be f of x plus h minus f of x. That's the change in the y's over the changes in the x. Now here, the x's will cancel and you get h. This is called the difference quotient, and this represents the average rate of change over that interval from between x and x plus h. But then what we're going to do is we're going to let h approach 0, and this q will approach p, and we'll end up having the tangent line. So that's what we're going to do. So the slope of the tangent line to the graph of f at a point x comma f of x is given by the limit as h goes to 0 of f of x plus h minus f of x all over h, if it exists, because limits don't always exist. Another way to characterize the same thing is the average rate of change of f over the interval from x to x plus h, or the slope of the secant line through those points, is given by this. Sometimes this is called the difference quotient in your algebra classes. So what we're going to do is the instantaneous rate of change of f at x, or the slope of the tangent line to the graph at x, f of x is the limit as h goes to 0 of that. These are the two same expressions. This is what it means as a graph. This is what it means in terms of change, rates of change. This is so important we give it a name, and this is the derivative of a function. The derivative of a function f with respect to x is the function f prime, where f prime of x is equal to this limit. The limit is h goes to 0 of f of x plus h minus f of x, all divided by h. The domain of f prime is a set of all x for which this limit exists. This is what we're going to spend a great deal of the time in this course studying. So you want to understand the limit definition and understand the notations that we will have. In fact, you'll also want to understand the geometrical interpretation, which is it's the slope of the tangent line to a curve. Other notations for the derivative are these. This is used in differential equations more than in this course, but dy dx is used often, and y prime is used often as well. You have to get used to these notations as well. So we have a four-step process for finding f prime using the limit definition. We will have fancy theorems later, very soon in fact, but for right now this is the way we're going to do it, and I will plan on assessing you, making sure that you understand this. So the four steps are: you compute f of x plus h. So we have f of x, we plug in x plus h there. And then we're going to compute the difference, f of x plus h minus f of x. And then we're going to take that answer and we're going to divide that by h. And then we're going to take the limit. Now you see we do all of these steps and then we take the limit, where we learned that in previous lectures. You see calculus continues to be the study of limits. So here is another problem. You find the slope of the tangent line to y equals f of x equal 3x plus 5 at any point. You know what to do. Let's see how you did. So we're going to use the four steps. So here's the first step. We're going to take this f of x and we're going to plug x plus h in. So this is 3 times x plus h plus 5. We simplify that and this is what we get. Then we're going to take this and subtract off f of x. Now notice we're subtracting off the whole of f of x. That's important, so you need those parentheses. And when you do that, the 3x plus 5 will cancel, and you're just left with 3h. Then I'm going to divide that by h. I will get 3, and the limit of 3, as h goes to 0, is just 3. Now we actually should have expected this result, since the tangent line to any point on a straight line must coincide with the line itself and must have the same slope as the lines, and the slope of this line is 3. Here's another problem for you to consider. This time y equals f of x equal x squared. You are this time to compute first f prime of x using those four steps, and then you compute f prime of 2 and interpret your results. 1, 2, 3. You know what to do? Let's see how you did. So we use the four steps again. Now when we put f of x plus h into the function itself, that's going to be x plus h whole squared, which is going to be this. There is a middle term. You're going to subtract off f of x, and we're subtracting off just this time x squared, but it's always the whole of f of x that you subtract. And when we do the algebra, we will get this for that difference, and then we divide it by h. Now we factored out the h from this because we're going to be taking the limit and the h's will cancel, so we get 2x plus h, and the limit as h goes to 0, that is 2x. Now that means that at any point x, f prime of x is 2x. So now what we can do is we can substitute 2 in, and this is not going to be a function like this. This is going to be a number, and that is the slope at this point. Here's another example. Let y equals f of x equal x squared minus 4x. You're to find x prime. This time we're going to find the point where the tangent line is horizontal. Sketch the graph and say what is the change of f of x at this point. Quite a bit to do here. You know what to do. We'll see how you do in 14.1.